Something is watching the sky. Every 30 seconds, without fail, without rest, without mercy, it opens its eye and stares into the darkness, not searching for beauty, not hunting for wonder, hunting for threats. And in less than 2 years of existence, before it even officially started its real mission, it found over 11,000 things we never knew were out there. 11,000 rocks, shadows, and silent killers drifting through space, some of them near Earth, most of them unknown. And scientists are calling this just the tip of the iceberg. So ask yourself, if this is just the beginning, what exactly are we about to find? There is a mountain in northern Chile, rising 8,800 feet above sea level into some of the clearest, darkest skies on the planet. No city lights, no atmosphere to speak of, just cold, thin air and the total, unforgiving blackness of the universe stretching above it. At the top of that mountain, a building sits like a sentinel, its dome rotating quietly through the night. Inside it is a machine unlike anything humanity has ever built. It has an eye measuring 8.4 meters across. It carries the largest digital camera ever constructed by human hands, a 200 megapixel monster so vast and sensitive that a single image it captures would require 1,500 pondered television screens to display at full resolution. And every 40 seconds it blinks. Every 40 seconds it swallows another massive slice of the southern sky, processes it, analyzes it, and searches for anything that moved, exploded, appeared, or vanished since the last time it looked. This is the Vera C. Rubin Observatory, and it just started one of the most ambitious projects in the history of science. What it is already finding should make every person on this planet pay very close attention. Most people have never heard this name, Vera Rubin, and that by itself is a quiet injustice that the scientific world has been wrestling with for decades. In the 1970s, while studying the rotation of spiral galaxies, Vera Rubin and her colleague, Kent Ford, made an observation that shattered the known rules of physics. Stars at the outer edges of galaxies were moving just as fast as the stars at the center. That should be impossible. Under every known law of gravity, those outer stars should be orbiting slowly, like the outer planets in our solar system orbit the sun slowly. But they were not. They were screaming around their galaxies at full speed, as if something massive and invisible was gripping them. Something that had no light, emitted no radiation, reflected nothing, and could not be seen by any instrument then in existence. Vera Rubin had found the most convincing evidence of dark matter ever gathered. She calculated that this invisible substance had to outnumber visible matter by a ratio of 10 to 1 inside spiral galaxies. 10 to 1. That means for every star you can see, every nebula, every planet, every asteroid, every atom of gas, there are 10 more units of something else entirely. Something we still cannot explain, something that is shaping the architecture of the entire universe, and we have no idea what it actually is. She spent her career trying to understand it. The Nobel Prize Committee, inexplicably, never awarded her its prize. She died in 2016, and in her honor, the most powerful ground-based telescope ever built was named after her. Because the machine that carries her name is designed to finish what she started. But here is where it gets complicated. When the Rubin Observatory began opening its eye to the sky, it was not only looking for the slow, deep mysteries of dark matter and dark energy, it was scanning everything, constantly. And the first thing it revealed was not something philosophical or abstract. The first thing it revealed was a problem far more immediate. A problem that exists right here, inside our own solar system, right now, in the present, in the dark space between planets that we have been calling our home for all of human history. Think about what we thought we knew. Before Rubin turned on, scientists had cataloged approximately 1.45 to 1.5 million known asteroids in our solar system. That sounds like a lot. It sounds thorough. It sounds like we had done our homework. We had not. During a 6-week test run, not even the real survey, just a warm-up period to optimize systems and test software, the Rubin Observatory conducted 1 million observations and discovered 11,000 asteroids that nobody knew existed. 11,000 new rocks in our solar system found in 42 days before the main mission even formally began. The International Astronomical Union's Minor Planets Center confirmed the discoveries. It was the largest single batch of asteroid submissions the center had received in over a year. And when the lead scientists at Rubin were asked to comment, they used a phrase that should send a chill down your spine. They called it the tip of the iceberg. Understand what that phrase means in this context. The full legacy survey of space and time, the actual 10-year mission that officially launched on June 30th, 2026, is expected to discover up to 500,000 new solar system objects per year of operation. Per year. Over 10 years, the Rubin Observatory is projected to triple the total number of known asteroids in the solar system. Triple. What we thought we knew about the inventory of objects orbiting our sun is, by the scientific community's own admission, deeply incomplete. We have been living inside a solar system we did not fully understand, surrounded by objects we never counted, orbiting in paths we never mapped. And now, for the first time in history, we have a machine powerful enough to show us what was actually out there all along. Among the 11,000 new discoveries, 33 were classified as near-Earth objects. This category has a very specific and unsettling definition. A near-Earth object is any asteroid or comet whose orbit brings it within 1.3 times the distance between Earth and the Sun. These are not objects comfortably far away in the asteroid belt, minding their own business between Mars and Jupiter. These are objects whose paths through space bring them into our neighborhood, some regularly. The largest of the newly discovered near-Earth objects measures approximately 500 meters across, nearly 8 football fields of solid, rock and metal traveling through space on a trajectory that crosses Earth's orbital zone. Scientists are careful to note that none of the 33 currently pose a confirmed impact threat. But read that sentence again very carefully, because what it also tells you is this: we only just found them. These 33 asteroids were there before we looked. They were crossing our orbital path before we found them. The question that haunts planetary defense scientists is not whether the 33 currently known ones are dangerous. The question is, how many more like them are still out there, unnamed and untracked, that Rubin has not yet found? And the numbers suggest there are many. Scientists estimate that we have currently identified only about 40% of what are called mid-sized near-Earth asteroids, objects larger than 140 meters across. Objects in that size range, if they impacted Earth, could cause significant regional destruction. Not extinction level, not the kind that ends civilization in one blow, but the kind that erases a city, the kind that devastates a coastline with a tsunami, the kind that changes weather patterns and kills crops across an entire continent. 40% identified. That means 60% of the mid-range threats to this planet are still unknown to us. They are out there right now in the dark, on orbits we have not calculated, carrying energies we have not measured. And the Rubin Observatory is the first instrument in human history with the sensitivity to find them, 6 times more sensitive than any asteroid search telescope that came before it. But the asteroid story, terrifying as it is not even the deepest layer of what Rubin is doing. To understand the full weight of this observatory's mission, you have to step back from our solar system entirely, look outward, and confront something that the entire framework of modern physics depends on but cannot explain. Dark matter and dark energy together make up approximately 95% of the universe. Let that sink in. Everything we can see, every galaxy, every star, every planet, every atom in your body, is 5% of what exists. The other 95% is invisible, undetectable by any direct instrument, and understood only through its gravitational effects on the things we can see. Dark matter, making up about 27% of the universe, acts as a kind of cosmic skeleton. It does not emit light or absorb it. It does not interact with electromagnetic forces the way ordinary matter does. But its gravity holds galaxies together, shapes how matter clusters into the cosmic web of filaments and voids that forms the large-scale structure of the universe, and, as Vera Rubin showed us 50 years ago, keeps the stars of spiral galaxies from flying apart into the void. Dark energy, comprising approximately 68% of the universe, is even stranger. It is the force, or property, or phenomenon, nobody is sure exactly what to call it, that is causing the universe to expand at an accelerating rate. Not just expanding, accelerating. The universe is not slowing down after the Big Bang. It is speeding up. Something is pushing it apart, harder and harder with every passing moment, and we have no idea what that something is. These are not minor footnotes in physics. These are the 2 largest components of reality, and science cannot tell you what they're made of. The Rubin Observatory exists in large part to attack this ignorance directly. Its primary weapon is a technique called gravitational lensing. When light from a distant galaxy travels toward us, any massive object in its path, including invisible dark matter, bends that light. It distorts the image we see. The shape of a distant galaxy as viewed from Earth is not necessarily its true shape. It may be twisted and stretched by the gravity of dark matter halos and filaments that lie between that galaxy and us. By mapping billions of galaxies and measuring the subtle distortions in their shapes across the entire southern sky, repeated hundreds of times over a decade, Rubin can build the most precise map of dark matter ever created. Not a guess, not a simulation. An observational map built from real light, showing where dark matter is distributed across cosmic scales, how dense it is, how it clusters, and critically, how it changes over time. Because if dark matter is not static, if it is shifting, clustering differently as the universe ages, that tells us something profound about the nature of dark energy and the ultimate fate of the cosmos. To disturbance. If a clump of dark matter passes through or near a stellar stream, it leaves a mark, a gap, a kink, a disruption in the otherwise smooth flow of stars. By hunting for these tiny deformations across hundreds of stellar streams, Rubin can detect the presence of dark matter, clumps too small and too diffuse to be seen any other way. It is like looking at a pond and inferring the presence of something beneath the surface, not by seeing it directly, but by watching the ripples it creates. Scientists believe a spherical halo of dark matter surrounds the Milky Way, filled with substructure, smaller clumps within the larger halo, arranged in ways that depend on the fundamental particle physics of what dark matter actually is. Rubin's precision could, for the first time, narrow down not just where dark matter is, but what it is made of. That would be one of the greatest scientific achievements in human history. And there is still another layer. Beyond the question of dark matter and dark energy, Rubin is already generating something unprecedented in the history of astronomy, a real-time alert system for the entire changing sky. On February 24, 2026, the observatory launched what it calls the Rubin Real-Time Discovery Alert Stream. On its first night of operation, it flagged 800,000 separate astronomical events. 800,000 changes in the sky, detected, processed, and transmitted in a single night. That number is expected to grow. Once Rubin is fully optimized, and the legacy survey is running at full power, the alert system is projected to generate up to 7 million alerts per night. Every alert is a change, something that moved, brightened, dimmed, exploded, or appeared where nothing was before. Some of those alerts will be known phenomena, variable stars, supernovae, known asteroids on predicted paths, but some will be new. Some will be things the algorithms flag as anomalous, things that do not fit existing categories, things that force scientists to look harder and think differently. Over 10 years, with trillions of individual measurements and billions of cataloged objects, the probability that Rubin will encounter something entirely outside existing scientific frameworks is not zero. According to the observatory's own team, they expect to find entirely new phenomena that have never been seen before, things outside the current vocabulary of astrophysics. The data volume alone is staggering. Every night, Rubin's camera generates approximately 20 terabytes of raw data. Over the full 10-year survey, the total data set will amount to approximately half an exabyte. To put that in context, that is 500 million gigabytes. The entire final data set will contain measurements for billions of individual objects, with trillions of data, points across time. No single human brain, no single institution, no single country can process that alone. The data will be made publicly available to the global scientific community and, in an unprecedented move, to the public at large. Thousands of researchers worldwide will analyze it simultaneously. Machine learning algorithms will scan it for patterns too subtle for human eyes. The Rubin Observatory is not just a telescope. It is the largest, most comprehensive data generation machine in the history of ground-based astronomy, and its output will fuel scientific research for generations. What makes this particularly powerful, and particularly unsettling from a planetary defense perspective, is the speed. What used to take years or decades to discover, according to the lead scientist of Rubin's solar system team, Mario Juric, Rubin will unearth in months. In just 6 weeks of test operations before the main survey began, 11,000 new asteroids. In one night of real-time alerting, 800,000 detected events. The universe did not suddenly become more dangerous the day Rubin turned on. The danger was always there. The rocks were always there. The gaps in our solar system inventory were always there. What changed is that now we can see. And the act of seeing, when what you are seeing has been hidden for so long, produces a very specific kind of vertigo. A recalibration of risk, a sudden confrontation with the scale of what we did not know. There are also objects that go far beyond near-Earth asteroids. Among the 11,000 new discoveries were 380 trans-Neptunian objects, icy bodies orbiting in the cold, dark, well beyond Neptune, in a zone of the solar system we have barely explored. 2 of them, given the provisional designations 2025 LS2 and 2025 MX348, have orbits so elongated, so stretched and eccentric, that at their farthest points from the Sun, they reach distances approximately 1,000 times greater than Earth's distance from the Sun, 1,000 astronomical units. These objects are moving through the most remote, most poorly understood regions of our solar system, in territory where the gravitational dynamics are still being worked out, in territory where, according to some scientific models, an undiscovered 9th planet may be lurking. Planet 9, a hypothetical world, larger than Earth, whose gravity is suspected to be tugging on the orbits of distant trans-Neptunian objects and pulling them into strange, clustered configurations that cannot be explained by the known planets alone. Rubin is now the best instrument in existence to either confirm or definitively rule out Planet 9. If it exists, the Legacy Survey should find it, and if it does not find it across 10 years of exhaustive southern sky coverage, that too will be a profound result. one that forces theorists to rethink the outer solar system models entirely. The first peer-reviewed paper using Rubin's data has already been published. It identified an asteroid, catalogued as 2025 MN45, that is nearly 500 meters long and spins once every 2 minutes. 2 minutes. To put that in perspective, most asteroids this size have what scientists call a fast rotation limit of 2 hours before centrifugal force tears them apart. This asteroid is spinning 60 times faster than that limit, which means it cannot be a rubble pile, a loose collection of rocks and dust held together by gravity, which is what most asteroids are. Something else is holding it together: internal structural strength, cohesion that goes beyond simple gravity. The implications for planetary defense are significant. If an asteroid like this were on a collision course with Earth, the standard response of breaking it into pieces with a kinetic impactor might not work the way models predict. It might simply fracture differently, or not at all. The science of how to stop these objects depends on knowing what they are made of and how they hold together. Rubin is now giving us that data at a scale never before possible. On June 30th, 2026, the Legacy Survey of Space and Time officially began. Not a test, not a warm-up. The real thing. 10 years. The entire southern sky scanned every few nights without interruption. A new detailed image captured every 40 seconds, around the clock, night after night. The observatory's project head described it as filming the greatest cosmic movie ever made. A living, evolving, dynamic record of the universe as it actually is, in motion, in change, in time. And that description is accurate, but it undersells what this movie might reveal. Because the universe is not a comfortable place. It is not static, not benign, not arranged for human convenience. It is violent and ancient and vast and mostly invisible to us, and we have spent the entirety of human civilization looking at it through instruments that could only show us 5% of what is actually there. Now that fraction is expanding. Now the view is widening, and what is emerging from the dark is not entirely reassuring. The terrifying thing about the Vera Rubin Observatory is not what it has found so far. It is the logic of what it will find. If a 6-week test run produced 11,000 unknown asteroids and 33 unknown near-Earth objects before the main survey even started, what will 10 years produce? If a single night of alerting captured 800,000 cosmic events, what anomalies are buried in those numbers waiting to be decoded? If the observable matter in the universe accounts for only 5% of what exists, and we are now building the most precise map of the remaining 95% ever attempted, what will that map reveal about the forces shaping our fate? And if Planet 9 exists, silent and massive in the outer darkness, what does its gravity mean for the long-term stability of the orbits of everything inside it, including Earth? None of these questions have answers yet. That is the point. The Rubin Observatory is not giving us comfort. It is giving us clarity. And clarity, when it reveals the true scale of the unknown, can feel very much like fear. The survey has begun. The eye is open. Every 40 seconds, another piece of the sky is swallowed, processed, and analyzed. The universe is being read at a speed and resolution it has never been read at before. And somewhere in that data, in those trillions of measurements, those billions of objects, those 7 million nightly alerts, something is waiting to be found that will change how we understand our place in all of this. Not if, when. The only question left is whether we are ready for what the darkness is about to show us.